Okay, thank you. So let's pick up from where we left. So we had started talking about L sheaves and L functions. We didn't actually talk about L sheaves yet. And I started explaining, I should have put the title here. So I started explaining the linear case. So the linear case means when we actually have a linear local system on our curve. So this is supposed to be a local system. And then you can think of it if you want as a unramified Langlands parameter. The L function at 0 is the trace of Frobenius, the alternating trace of Frobenius on graded symmetric powers of the cohomology. Recall graded symmetric means exterior for H1. Another comment I wanted to make and forgot is that this 0 is kind of a red herring. It doesn't really exist. What I mean by this is that you can change the 0 to 1 by twisting your Langlands parameter by the cyclotomic character, right? You can twist by, so this is a red herring here. You can just, we write 0, but we really don't mean L function at 0 in the classical way of normalizing L functions, because this classical point of evaluation can be incorporated in the local system itself. Okay, so can always change the Langlands parameter by a central character into GLV, GLX. X here is the fiber of that at some base point. And of course, it's kind of important here that we don't use the Galois version, but we use the veil version of the Langlands parameter so that we can twist by characters that are not finite. Okay. Okay, so really you're going to see many L functions in the rest of my talk, and they will always be encoded into something like that, but you shouldn't necessarily think of them as a central, as an L value at 0, because where the L value is really evaluated is part of the Langlands parameter, and also it will be encoded in some GM action on our spaces. Anyway, I'll get to this later, just a quick preliminary comment on that. Okay, now, in the setting where in the setting where we have a reductive group, and and x tilde, which is a linear local system, comes from a G bundle plus representation. So in the same way that I described earlier on the band G side, so suppose that you have, sorry, not G bundle, but G local system. So there's a notion of G local systems. Galois, theoretically, you can think of them as pi1 mapping to G, and then this will be combined with a representation from G to GL of some vector space. Consider this representation as being fixed, but consider the local systems as varying. So you have some space, moduli space of local systems, which is an essential piece of the geometric Langlands picture. So so then the corresponding linear local system also can vary over systems, vary over the stack of G local systems. Sorry, I think I didn't say. I think maybe I've mixed you. I mixed you up here. So let me say it again. Let's start with some fixed representation of the group G, okay? And now we combine it with arbitrary local systems in order to get a family of local systems, varying as the G local system varies, okay? And then that means that we get a family of cohomology spaces. Okay, so we get a family of cohomology spaces and their symmetric powers. Varying over rho in here. Okay, and I was explaining earlier today that these symmetric powers of the cohomology, I want to think of them as functions on some derived space, the space of global sections. So earlier today, I said that I want to interpret this as the trace of Frobenius on functions on the derived space of global sections. So the classical space of global sections is just H0. And here I should dualize the bundle, I guess. So this is the dual bundle. So the classical space of global sections is H0. The derived space of global sections includes the higher powers, the higher cohomologies. Okay, and this is viewed as some kind of derived scheme. When we write functions on this scheme, it's the symmetric powers of its dual. In this case, so it's exactly this. That's as a reminder. So similarly, when you do things in families, with some amount of faith in derived algebraic geometry, so in families, there is some derived stack log Gx over log G, whose fibers are precisely these derived sections, whose fibers are precisely those derived schemes of sections gamma sigma x dual, and here I will put a an index just to denote that this lives over, this is the fiber over some G local system. And by the way, everything I'm saying here is on the spectral side. So this G is the dual to the G that came up with periods earlier. Okay, I don't want to keep writing G check. So now G is on the spectral side. Coordinate ring of this scheme, or up to some shifts that I will explain in a moment, this coordinate ring, which is interpreted this way, this is going to be what we call the L-sheaf. Okay, so more precisely, let me use pin here for this projection map. So the definition is that the L-sheaf, so given a representation from G to GL of some vector space X, the L-sheaf the L-sheaf L sub X on the moduli space of G local systems is the push forward of the dualizing sheaf of the dualizing sheaf on log G X. And here everything is in the coherent setting. So now when I say sheaves, I will not write this sheaf. This is quasi-coherent. Yeah, so I think that, so this is cooked up so that it's Schrick fibers are these symmetric powers of cohomologies of the local systems varying with. So I would suggest not worrying too much about whether this is the dualizing sheaf or the structure sheaf. It doesn't matter too much. And why we're using the dualizing sheaf? In fact, in order to see why we're using the dualizing sheaf, you need to consider some well, it's a little bit. It took us a few years of until we realized we should be using the dualizing sheaf. But you can already see it when you do Tate's thesis that here you need to put dualizing, but it's not very, the difference is not very important. Over an open locus, those two will just vary by just some cohomological shift. So it's really not so important. The important thing is that the fibers of this sheaf are these spaces, maybe up to some homological shifts. This geometrizes the L function, because if you now take trace of Frobenius, you get the L function, or the special value of the L function. So hence it, because the fibers are these, by taking trace of Frobenius, you see that this geometrizes the L function. And the idea now is that so in geometric Langlands, you have something like constructible sheaves on band G are equivalent to, there's an equivalence of categories between this and some version of coherent sheaves on G-check local systems. And I'm skipping a lot of decorations here. There is something about nilpotent support. So the statement that I'm about to make, you cannot directly make. You need to apply some nilpotent projectors. Depends also on which version of geometric Langlands you're interested in. There's the RAM version, there's Betty version, there's a TAL version, different decorations in each one of them. I'm not going to bother you with those, not for your own sake, but for mine. So the idea and hope is that a certain period sheaf under this equivalence matches with a certain L sheaf, and this geometrizes the equality between periods of automorphic forms and L functions. This kind of statement directly translates after trace of Frobenius to a statement relating periods of automorphic forms and L functions. But I have only explained the L sheaf in the linear case. It gets interesting if we start thinking about nonlinear spaces. So you already, forget about sheaves for a moment, let's think about L functions. You already knew that a linear representation of a group G gives rise to an L function. That's the definition of Langlands L functions, right? This is the dual group of whatever you are thinking of. So Langlands told us that for every linear representation of the group, you can attach L functions to automorphic representations, right? So what about the nonlinear case? So this point of view suggests that there is a way to generalize the definition of Langlands. What I did? Okay. No, not this one. So the polarized nonlinear case. So here I'm going to take X to be not a necessarily linear space, but some G space. I just want to assume for now that X is quasi-affine and smooth. Actually, I don't think I'm going to use quasi-affine here. So this point of view of fixed points or sections, what are sections? So let's go back to, sorry, there's one more thing I wanted to say. And that was before, yeah, so suppose that I have last time I had written this short exact sequence, pi1 geometric, pi1 Galois FQ bar over FQ. So when we take cohomology, we take cohomology over the geometric curve. And when we take sections, what do sections mean in terms of a Langlands parameter? So if you have a local system, that's defined by some representation like this, okay, you restrict it to the geometric fundamental group. So let's call it phi geometric. But then what does section mean? Section means invariance, points on x fixed by this action, right? Because x is the fiber of the local system at some point. This is the monodromy representation. So if you have a section, it has to be fixed under the monodromy representation. So sections are the same thing as fixed points. X fixed by phi geometric. Okay, so, and derived sections is some derived version of fixed points. Okay, so this is what I want to generalize. So in the nonlinear case, so we can define, so given a Langlands parameter phi from the Galois group. Here, let me say something, not necessarily in the function field case, okay? So Galois group of our field to G, we can define the L function associated to this data, which is now like a Langlands L function, but without a linear space. And again, we have this red herring here, which is the point of evaluation. This is going to be not a single L function, but it's going to be a sum over the fixed points, which I'm assuming to be discrete. I'll write the assumptions in a moment. It's going to be a sum over fixed points by the parameter of some L functions, which will be the corresponding L functions. So suppose that I have, so Galois maps to G and acts on the space, okay? So that's what I mean fixed points. Now, for every fixed point, we have an action on the tangent space of that fixed point. So I'm gonna take the L function associated to my parameter, acting on the tangent space of that point, and now that's a honest linear L function, Langlands L function, and this is going to be my definition of L function in the nonlinear case. This makes sense at least when this set is discrete. When it's not discrete, we should be thinking about, when it's not discrete, that means that we are at the pole of an L function, because already in the linear case, when this is not discrete, you have a pole of the L function, right? That means you have the trivial representation somewhere there, okay? So when not, we think of the L function as having a pole. At 0. Any questions? So this geometrizes to, yes. Yeah, not really. I mean, except that rho was phi geometric. Yeah. Yeah, you're right to call me out for that. Rho was phi geometric. Any other questions?
So in that case, in the original rectangle there, you were working on rho, the fixed point of x under rho.
Yes.
Here you sort of use the whole
Yes.
How do you reconcile it?
That's not a problem because of what I said about poles of L functions. So you can imagine, take for example, the trivial geometric parameter for GL1 with the standard representation on A1. Okay? So in that case, you have a non-trivial H0 geometrically. Okay? But then when you write a non-trivial H2, so you have denominator. But then when you write trace of Frobenius at 0, you're going to get a pole. But if you twist the action of Frobenius, like I said, the 0 is a red herring, then well, then you have, arithmetically, you have isolated fixed points, just the 0 point. Okay, geometrically, you may have more fixed points, but arithmetically, you just have the 0 point. Okay? And since you have twisted the parameter, this here is secretly an S. So here you get the zeta function at S. If you don't twist the parameter, then the zeta function is infinite. And that's it. Did it make sense? Yeah. So I didn't require, over there geometrically, I didn't make this requirement that the fixed points are a discrete set. You can have H0, you can have H2. Here, arithmetically, I said, okay, let me give myself a discrete set. Let's assume that this is a discrete set to make sense of it. Otherwise, I have a pole.
When the fixed points are null states, does it matter if they have some succession or similarity or whatever?
So it is a very good question to whether we can understand L functions even at the poles where they have at the points where they have a pole, because at least in the geometric setting they become something interesting and non-trivial. But I don't know how to describe them. I don't know. I haven't thought very much about that. So the geometry. Any other questions?
How rare is it?
How?
How rare is it? How can you make it?
So arithmetically, discrete points means no poles for the L functions.
Yeah.
Okay. So typically, when you have the freedom to twist your suppose that not every group, of course, has a central character, right? A central co-character. But typically, like in these Rankin-Selberg integrals, very often you have some continuous parameter that you can play with. Okay, then you can always make this condition work for some values of S, and then you get the L function, and then with poles. Okay, so this has this geometric story, which I'm not going to say much about. Just, I'll say, have faith in derived algebraic geometry. So, again, this is just the moduli space of G local system G and sigma section of the corresponding X local system. So this is some kind of derived stack, and then the L sheaf is going to be defined as the push forward, the star push forward of the dualizing sheaf. This is the definition. And then if you have an arithmetic local system, and you compute trace of Frobenius on its fibers, on the fibers of the L sheaf, you recover this kind of number. Okay? Okay, so now I would like to do two things. The first thing I want to do is to give you some examples, not in the geometric setting, already in the function field function theoretic setting, where this point of view shows up in automorphic forms. And where, you know, and particularly in the study of periods, where dual to a period, you don't have an L function, but you have a sum of L functions. So I'll give you some examples of this, and then we will discuss the non-polarized case. As you see here, I haven't said anything about the non-polarized case. I always assume that G is acting on a space X. What if instead of X, I have what is morally its cotangent bundle, but it's not the cotangent bundle of any space? Some kind of Hamiltonian space that's not polarized. And that's where we will get to the Clifford algebras that were mentioned in the first conjecture that I mentioned in the morning. But let me give you some examples of what this kind of yeah, maybe I was allowed to use the sideboard, so maybe I will leave those here for now. And I will tell you examples of sums of nonlinear L functions in nature, where of course nature means periods of automorphic forms. So first of all, most people in the audience, I'm sure, are familiar with the Ichino-Ikeda conjectures for the Gross-Prasad period. Okay, so for certain periods, like SO, we're back to the period side for a moment. Okay. So this is the classical Gross-Prasad period, or even the Whittaker period. So G mod out by the maximal unipotent subgroup, but with a non-degenerate character. So this is Gross-Prasad. This is Whittaker. There are precise formulas or conjectural formulas of the form global period square is equal to an Euler product of local periods. And these formulas, well, I mean, the prototype of those was already proven by Valproget, but then Ichino and Ikeda organized known examples and realized that there is such a general formula. And in the Whittaker case, the analog of the conjecture has been formulated by Lapid and Mao and proven in some cases. So the global period is an Euler product of local periods, except that the conjecture does not look like that. Partly it doesn't look like that for trivial reasons. This Euler product is some L value at a half. The product doesn't literally converge, but okay, you can make sense of the Euler product using L functions. That's not the issue. Another issue is that here you have a factor, all of the factors are local except for one, which is something like 1 over the size of the Langlands, of the centralizer of the Langlands parameter. So this is the size of the centralizer of the Langlands parameter, which here I'm assuming to be discrete. So centralizer of the Langlands parameter. A priori, it's very mysterious how this appears. Now, let me tell you how this is explained in the relative Langlands duality picture. So, there's an explanation of this factor via relative Langlands. But this explanation says nothing at all about these periods. This explanation is about the group case. The group case is when we have a space which is a group. I'm going to denote it by H because the group acting on it is H cross H by left and right multiplication. So, what is the period shift? So the period, what is the period function in theta series? Well, if you integrate them against automorphic forms, basically you're computing the diagonal. So this is H cross H mod H diagonal, right? That's what the space is. So basically you're computing the integral over the diagonal. You're computing inner product. Okay, so the inner product between period functions and automorphic forms, so period of automorphic forms for this space is equivalent to computing inner products, right? So that's what the period problem is here. And now, what is the dual? So I haven't said anything about the duality, but we'll believe now that this space has a dual. And let me assume for simplicity that H is split. So the dual is going to be X dual equals H dual under the action of G dual, which is H dual times H dual. So here the action is not exactly the one you think. One copy needs to act twisted by Chevalier involution. So but if you want, you can completely ignore that. So now, take it for granted that this is the dual variety. So, if I want what the conjecture will say that so the period L-function duality should say that what should it say? It should say, again, I haven't given you any precise statement about how periods are related to L functions, so take this. So I'll just tell you what it should say in this case. It should say that that periods of automorphic forms, and here really the automorphic form has to be, well, for an automorphic representation of G. So an automorphic representation of G is an automorphic representation of H and another automorphic representation of H. But okay, this period is going to be trivial unless one is dual to the other. So I can also say that pi is of this form. Okay? So the conjecture should somehow relate periods of automorphic forms over the diagonal subgroup H to the nonlinear L-function associated to this automorphic representation or to its Langlands parameter and the dual space X dual. Let me also put 0 here, but again, this is a red herring. So whatever period L-function duality you have, the analog of the Ikeda formula or whatever, should say that the period, the diagonal period, which is the inner product of two automorphic forms, should be related to this nonlinear L-function. But here we said that the dual space is just H dual. So what is this nonlinear L-function? It is a sum over fixed points. But what are fixed points of a parameter? Fixed points of a parameter correspond to the centralizer of the parameter. So this is going to be a sum over x in the centralizer of the parameter of the corresponding linear L functions. And what are the linear L functions? These are the L functions at the tangent space. Let me write them explicitly. Now it so happens that at every point in the centralizer of the parameter, you get the same representation here. You just get the adjoint representation. So you end up with S phi times the adjoint representation. And really, I mean, it's a little bit annoying to keep writing the 0. Sorry, let me completely erase the 0 because this is really a 1 for reasons I haven't told you, right? Because I haven't told you how the parameter is supposed to act on the dual vector space, or on the dual variety. So let's ignore this. This is really a 1 here. What this means is that when I write my global period as an Euler product of local periods, I should also insert this factor. That means when I factorize the global inner product in terms of local linear products, I shouldn't have an equality as we usually do very naturally, but I should have an equality up to this factor. If you correct, the local linear products appear in the Ikeda formula. So these local periods involve local linear products. Local matrix coefficients. If you correct for this, then this factor here will disappear from these conjectures.
So correct means frame 1. But usually as phi is not discrete, we take its group of connected components, you know?
Yes, and usually the inner product is not defined because the automorphic forms are not L2. So these two things go together. So it's very interesting to think about what this means for Eisenstein series. But yeah, there are two infinitudes here that come together.
And also, is the reason that the tangent spaces give you the same representation is that you have one orbit? Or is it?
No, it's simply the fact that you calculate what happens here at the fixed points. If you it's still the same representation, still the adjoint representation. It's just a calculation. It's.
So this double arrow, does it mean that the square of the right hand side is equal to that?
No, because the left-hand side depends on the choice of vector. So to make this precise, I need to write something like global period is equal to product of local periods. And all I'm saying is that if you want this to be compatible with our with the framework of relative Langlands duality, I should write this global. So global inner product is equal to this factor times an Euler product of local inner products. Okay, so let me maybe, to demystify it a little bit, let me say that pi is tau tensor tau dual, and then I fix an Euler factorization as a restricted tensor product of tau. Okay, now I want to fix unitary structures. Okay, so I want to fix to write down this period means to write down okay, so I need to fix, this is an abstract isomorphism of representations, and I want to make it to say how so this is an automorphic representation, so it comes with a global automorphic product, and I want to specify how I want to fix this isomorphism. And I'm saying that I want to fix it in such a way that the global automorphic product is this factor. Okay, this should really be the centralizer of tau here. Okay, let me not worry about this. Times the product over all places. Yeah, so this should be the centralizer of tau, I'm sorry. A product of all places of the local inner products. Okay? I can choose to do that. I'm not doing anything here, right? This is kind of tautological. I'm telling you that this is how you should fix it, because that's going to be compatible with relative Langlands duality. You need to fix it this way in order for to make our conjectures work, which in this case, our conjectures are just a matter of choice. I mean, the conjectures are all, depend all on some kind of normalization. And I'm telling you that you should normalize the inner product this way. If you normalize the inner products this way, the Ichino-Ikeda conjectures use this local inner product. But the way they are stated, of course, they are stated under this assumption. If you change this, your convention, then the factors disappear from there. So these factors really have nothing to do a priori with, I mean, from the point of view of relative Langlands, these factors have nothing to do with these periods. They have to do with the group period and with the fact that you have many fixed points in the group case. Okay, so now let me give you another example where periods are equal to sums of L functions. So the second example comes from the thesis of Shaolei 1 under Wittek.
So is it because on the left-hand side there is a global period square over the inner product of the form with itself?
So here I'm not changing anything, but when I define local periods, they're given as integrals of matrix coefficients.
What I mean is relation to the L function is the ratio between the global period and the inner product of the form with itself.
I mean, there is an L function hiding here, and it includes this adjoint L function in the denominator. So yeah, okay, yeah. All right. So he did. So in his case, he considered the case of x equals SO5 mod GL2. Actually, in the thesis, he considers forms of GL2 unitary groups. So, but let me, for simplicity, take the split form here. So, in this case, you have a dual variety for the dual group, and the dual group is SO4, and the dual variety is something like that, standard times SL2 times SL2 SP4. So the dual group is SP4. Inside of SP4, you have SL2 cross SL2. Okay? I could tell you that the dual space is SP4 mod SP2 times SP2, but that's not the case. It's a vector bundle over that. Okay? However, what do I mean by standard? By standard, I mean the two-dimensional standard representation of only one copy of SL2. Okay? So this is only, so the product here acts through only one copy. Okay? Now, what does he prove in his thesis? So his theorem maybe I will overstate it a little bit, but okay, so when an automorphic representation of G comes from, I want to say that the Langlands parameter a priori lands here, but I want the Langlands parameter to land here. Okay? So the way he constructs this is through theta lifting. Okay? But let me not invoke theta lifting. I'll just say that when an automorphic representation G has Langlands parameter factoring through SL2 cross SL2. Of course, we don't know what Langlands parameters mean in the global number field case, so the theta lifting is a way to define what I just wrote. Okay. Then the period over this subgroup H of automorphic forms in pi is a sum of two Eulerian distributions. So, so what does it mean for the Langlands parameter to factor through this? It means that the representation comes as a theta lift from pi 1 times pi 2 of PGL2, right? So, but which one do you call pi 1 and which one do you call pi 2? Here's the question. So it turns out that it doesn't matter because his formula, I'm going to write something like this, L pi 1 standard plus L pi 2 standard. This sign here really means, again, you have some kind of Ichinui-Ikeda type formula where this global period is written as a product of one Euler product plus another Euler product. Okay, and here I'm hiding some factors that come from denominators and things like that. But the essence of it is that here you see a sum of two L-functions, which again can be interpreted because by the fixed points of the parameter on this dual Hamiltonian space. Every ordering of pi 1 and pi 2 gives you a different fixed point. Okay, in order to have a fixed point, your parameter has to factor through here, but it can factor through here in two different ways. Okay, and maybe, maybe there are some cuspidality assumptions and things like that. It's not very significant right now. But that's another example where this kind of nonlinear L function, which is really a sum of L functions, shows up in nature. And let me tell you a third example. If I find my Yes, it's over there. So the third example comes from the work of Spencer. It's related to the relative endoscopy of Spencer-Leslie, and it is the following example. Consider X to be UN, so UN is a unitary group corresponding to some to some quadratic extension, split over a quadratic extension. So I'm going to take the restriction of scalars for this quadratic extension of GLN. So over the algebraic closure, of course, this is the group case. Over the algebraic closure, this is GLN square mod GLN. Okay? So we already said what the dual is in the group case. The dual in the group case is just the dual group. So it's going to be GLN mod GLN cross GLN. But you have a non-trivial action of the L group, so the same way that you have a non-trivial action of the L group on the dual group, of the Galois group on the dual group, you also have it on the dual Hamiltonian space. So, and it is induced by the action of the dual group. So the non-trivial Galois over F acts here. So when we write L functions, we need to take this action into account as well. Now suppose that the parameter from the Galois group to the L group of G fixes a point. Okay, parameters only matter up to conjugacy by the connected dual group. So without loss of generality, this parameter will factor through, so this parameter will fix the identity coset without loss of generality, which means that it factors through its stabilizer. So without loss of generality, the parameter factors through GLN. And this is a well-known phenomenon in this case, studied by Zagier in a series of very important papers for the relative trace formula. Zagier proved that for an automorphic representation to have non-zero period over the unitary group, it has to be base change from GLN. Okay, so that means that phi is base change from GLN. Okay, but now we want to have precise formulas for the period, or maybe for the period square. And again, Zagier started this project, and it was completed by Fagon, Lapid, and Offen, at least for cast forms. But there's actually something very interesting happening for Eisenstein series. So let's try to see what this nonlinear L function gives us. So what are other fixed points? So here, without loss of generality, I said that the fixed point is just the identity coset. Okay. So what are other fixed points? So, if the parameter is discrete, The only other fixed point is, well, here I had +1. The other fixed point is going to be, so what is +1? +1 is +1 here, +1 here. If the parameter is discrete, the only other fixed point will be, I want to say 1 minus 1, but what about the entire center? So, central, diagonal center doesn't matter. It's still in the same coset. So it's 1 minus 1 times GLN. Okay? And in this case, so for both of those points, the linear representation, so this tangent space is simply the adjoint, what is it? Just a second. Is simply just the adjoint representation twisted by, again, we have to take into account the action of the full L group. So over in the previous example, in the group case, we had just the adjoint representation. Here we twist because the L group acts non-trivially. So this is the quadratic character of E over F. Okay, so in other words, when you write down periods, okay, maybe there's a hidden factor of 2 because there are 2 fixed points if you are very, very careful with the constants, but you only see one L function. Okay, so Spencer was starting to prove his theorems and his fundamental lemmas and to formulate conjectures about relative endoscopy, and I started complaining because I told him the comparisons that you're making do not match with the predicted L function, which in this case is this. Okay? However, Spencer was right. And I only understood why he was right after BZSV, because if phi factors as phi alpha, phi A times phi B into GLA times GLB, where A plus B is equal to N, then there are more fixed points. And these fixed points are the following. They are plus minus 1A, that's the dimension of the general linear group, minus plus 1B, and then the same up to sign in the second copy. And if you calculate the linear representations here, you get something like GLA tensor eta plus GLB tensor eta plus standard A and standard B dual tensor eta plus standard A dual and so standard B tensor eta, something like that. And of course, if you decompose the adjoint representation of GLN in this case, you're going to see things like that. right? The adjoint representation, if you omit the etas, the adjoint representation decomposes like this. But what am I saying here? Sorry. Sorry, I think I've copied some factors wrong, because what I wrote down is the adjoint representation tensor eta. Some etas should be missing from here, and this is just standard representation of GLN. Yeah, sorry. These etas should not appear here. If I'm not mistaken by what I wrote in the next line of my notes, these etas should not appear here. I miscopied in my notes. Okay, so I'll check, and if it's incorrect, I'll correct it tomorrow. But you see that this is different from this now. Okay, and this gives rise to the endoscopic comparisons of Spencer. Basically, to do the endoscopic to see what you should be comparing with, you should divide everything by the adjoint L-function. So these factors here will disappear, and then you're going to get something like this over the adjoint L-function of this, and you recover as a prediction what Spencer had already proven.
This is the same as the adjoint L-function twisted for another factorization.
Sorry?
This is also the standard, the adjoint representation twisted by eta for another factorization. Or you twist
yes, other factorization means another fixed point, basically. Yes. Yes. But I fixed my factorization by saying I have one fixed point, and then, yeah. Yeah.
This aligns with the series of Einstein series.
I see. Okay, I didn't know that you had this input. This
example
That's right. Yeah, I mean, it is the same. Yeah, of course. I mean, look, fiber of base change is precisely the count of fixed points in this case. It's the same question on the side of Langlands parameters. Given a Langlands parameter, when I say how many fixed points, it's the same as saying in how many ways does it factor through a conjugate of up to conjugacy. But this up to conjugacy is counting fixed points. Yeah. It's exactly the same, yeah.
If we try to predict what special groups, what goes wrong, if instead of taking the endoscopic subgroups, say take non-endoscopic subgroups like GLA times GLB times GLC.
Sorry, for which case?
For that case, if I try to do it via your approach instead of starting from the endoscopy, why shouldn't they see the examples?
I am not sure what the proposal is.
What is the factors of CA times 3B times 3C?
Yeah, I mean, you study there the fixed points, and this is either related to the fiber of base change, as I was saying, or it will show up in endoscopy. Endoscopy doesn't necessarily mean you need to have two factors. You can have more factors there, I think. Huh? In your story too. Other questions? Okay. So, I'm not going to finish today, but I finished with my examples, and I have enough time to give you a sense of that conjecture that I wanted to get to. So I think I had part A, the linear case, part B, the nonlinear case, and part C is going to be the non-polarized case. What is the L-sheaf? L-sheaf or L-function. So let me explain first of all why the question makes sense. So we have certain relative Langlands duals. So I have a group G and a nice Hamiltonian space for G, and in many cases we can describe a dual group, a dual Hamiltonian space for G check. And one reason that we can describe it is, like, if you put this on the automorphic side, we've seen that whether it's polarized or not, doesn't matter. We can use the Veil representation if it's not polarized, and we can make sense of theta series on the automorphic side. And then we compute its dual, but now under relative Langlands duality, you should be able to do this the other way as well. So the fact that we know what duals are in many cases is because of that. Also because sometimes we don't have formulas for the L function, but we have formulas for the square of the L function. So let me give you the basic example of non-polarized. Let me give you the basic non-polarized example. It is the Gross-Prasad example that I had mentioned. So example, M is T star of SON times SON plus 1 mod SON. So theta series here and periods here, just periods over SON inside of the bigger group. And then the dual Hamiltonian space, well, the dual of this is, let's say for simplicity, let's say n equals even. So the dual is going to be the standard representation of the dual SON. Tensor with the standard representation of the dual of this, which is SPN. This is symplectic, this is orthogonal, so the tensor product is a symplectic vector space. So in that case, we know that this is the correct duality because of the Ichino-Ikeda Gross-Prasad conjecture that tells you that the square of the period over H is this subgroup, is related to the L function of this. So this is period associated to some automorphic forms, and is the L function of the automorphic representation for this representation of its dual group. Okay, and again, I'm suppressing the point of evaluation. This is a central L function. Tomorrow I'll talk about all of these things, points of evaluation and all of these things. So let me suppress them today. But when we say L-sheaf, on the other hand, geometrically, well, we have seen that this is the integral of the automorphic form against a theta series, but now I'm squaring it. However, the theta series itself makes sense, right? So before I say anything geometrically, so let me just say that this is the integral of some automorphic form against some theta series. And again, maybe I need to change the automorphic form, but you can rewrite it like this, that we explained in the beginning in the morning. And we've seen that this theta series, at least in the everywhere unramified setting on function fields, this is obtained through sheaf function dictionary from some period sheaf. So in unramified in the unramified geometric Langlands setting, we have a period sheaf P sub x, which is, in this category that geometric Langlands, one side of geometric Langlands lives on. And geometric Langlands is now a theorem. It was not when we were starting BZSV, but geometric Langlands tells you that there is a well-defined L sheaf corresponding to this period sheaf, which is some incoherent sheaf with some decorations on the space of local systems on the dual group. So if this space were polarizable, so this is not T star of X check for X check a G check space. If this were polarizable, I've already sketched how we define this L sheaf, and we conjecture that it is the geometric Langlands dual. Now what is it? There is some sheaf on the spectral side. We know it exists because of Gatescory and Raskin and company. But what is it? We cannot even predict it. This has an arithmetic counterpart, which is, what if I erase the square from here? What if I just take the period over h? Can I say something about its value? It's going to be some square root of the L function. Which square root? What is the correct square root of the L function that gives rise to, that corresponds to the period? Okay? And I have maybe 1 minute or 2 minutes. How much do I have? 1 minute? 2 minutes. Okay. So what we will see is that this conjecture that I wrote in the beginning, in the morning, in fact, I don't have much more to say towards this conjecture. I'll just repeat it tomorrow and give you the necessary definitions. But what we will see, well, we don't know what this L sheaf is, but at least we can predict what its endomorphisms are. So the conjecture is that endomorphisms of this L sheaf is, well, this is going to be some sheaf living over the moduli space of local systems, and we're going to say that the endomorphisms of this L sheaf is a certain sheaf of Clifford algebras. What did I say? Conjecture, oh no, that's 0,1 on my notes, to alpha 8,1. A certain sheaf of Clifford algebras at least over an open of log G check. So we cannot fully describe this, but we can describe its endomorphism ring, and we can describe its fiber. Well, I'll say a little bit about that tomorrow. This is a fantastic idea of Akshay Venkatesh's. I can claim no credit for this, so I can say that it's fantastic. It's in our paper, but it's like a fantastic idea of Akshay's. Okay, so let's continue tomorrow.